So on the worksheet called In-Class Energy, it's number 11. We had kind of left off somewhere right around here yesterday. So question number 11. It says a 2.5 kilogram block is dropped, keyword dropped, from a height of 1.2 meters onto a spring, and it compresses at 0.3 meters. What is the spring constant of the spring? So it's a two-location problem. So here's my location 1, here's my location 2. The biggest hang-up that I've had so far with students working on a problem like this is they are not defining, they're not being consistent with a height where they define their height to be 0. So they choose a height to be 0 at one location, but then at the second location they aren't consistently measuring to that height. So yesterday I kind of talked about some different options for height. I talked about if you put at the top of the spring your H to be 0 perfectly fine, then from here to here your H1 would be 1.2, and then from here to here would be negative 0.3. Perfectly fine, nothing wrong with it. Because I defined my height to be 0 right here, I need to consistently measure my height from that point. I said another way we could define our height to be 0 is at the lowest point, and I said that's the way I was going to set this one up. The nice thing about defining my lowest point to have a height of 0 is when we go through and talk about types of energy, 0 height means no potential gravitation, so it does kind of cancel out the next terms. But if this height is what I define to be 0, then my H2 is 0 because H2 is at 0, but my H1 is not 1.2 because I'm not asking how far is it from the spring to the block. I'm saying how far is it from 0 to the block. So it's how high is it from here to here, and then from here to here. So that's where that height of 1.5 meters is, because it's 1.5 meters away from my height of 0, where I defined it to be 0. We said yesterday that when we talk about spring stuff at location 2, there is a compressed spring, so therefore we want to address spring stuff. At location 1, we don't really need to worry about spring stuff, because is there a spring? You could say, yeah, it's 1.2 meters above it. However, that spring isn't compressed or stretched, so therefore there's not storing any energy. If you wanted to, you could talk about PEE at location 1, but when you do talk about spring stuff, your spring would not have, your X would have been 0 because it's not compressed. So in situations where work in is equal to 0 and our work done by friction is equal to 0, then we get a special type of problem called conservation of mechanical energy. And in a conservation of mechanical energy, ME1 is going to equal ME2. And ME1 is what we get when we take our potential gravitational energy at location 1 and I add it to my potential elastic energy at location 1, and I add it to my kinetic energy at location number 1. And we can set that equal to ME2, which is PEG2 plus PEE2 plus KE2. Then by looking through those, looking at our picture and kind of going and saying, hey, what are the questions we ask ourselves for these different types of energy? At location 1, we said there was a height. At location 1, we said there was no compressed spring. And at location 1, and the keyword was dropped, we said no kinetic energy. And I think we maybe got to the canceling out process yesterday, I don't remember.
We did not.
We did not, okay. At location number 2, we defined that to be a height of 0, so there is no PEG. At location 2, there is going to be a compressed spring, so there'll be a PEE2. And at location 2, because it's at maximum spring compression, there is going to be no kinetic energy. So this simplifies down to M times G times H1, which is equal to 1/2 K2 X2 squared. And I don't remember if yesterday I put like 2's and 1's next to K's. It's just a way that we can differentiate, because sometimes you might have more than one spring. So I'm talking about the spring at location 2. I'm talking about the spring constant of the spring at location 2. I'm talking about the spring displacement at location 2 of that spring. That's really all we're saying. So then we start plugging numbers in. Mass is 2.5, gravitational acceleration is 9.8. We defined H1, or we said H1 was going to be 1.5 because of where we defined our height to be 0. And that's equal to 1/2 our K2 value, which is what we're trying to solve for. What is our spring constant? And then that's going to be times how far that spring is compressed, which is 0.3 meters. And don't forget to square that value. That's a pretty common math error that is made. So 36.75 is what we get on the left-hand side when we multiply 2.5 times 9.8 times 1.5. And that's said equal to 0.045 K2. Then we divide both sides by 0.45 to get a K2 value. That's going to be equal to 816.67, and our units are newtons per meter. It's a 2-location problem. It's a 2-location problem as spring. Pretty common mistakes is people will say H1 is 1.2, but then they'd say H2 is 0. But it's below 0. So make sure you're consistent with your heights based upon your where you define your height to be 0. There's a part B to this, and really part B is just, it's another location. And these locations could really be any places in between. We could say how fast is an object moving when it's partially compressing a spring. We could say how fast is it moving before, like at some height up here. For part B, the question being asked is, so like if we have location number 3 over here, part B is saying like how fast is it going right before it touches the spring? So the key to the right before it compresses the spring is right before it compresses the spring, how much is that spring compressed? For spring stuff, right? Because does this spring have a spring constant? Yeah, we just calculated it. It's 816.67 newtons per meter. But how far is that spring compressed right before it touches the spring?
I'm not sure. It's compressed 0.
It's compressed 0, right? Because it's not touching the spring yet. So this is 0, which really means we don't really need any spring stuff. You're more than welcome to put it in there, but just realize right before it touches the spring means it's not compressed at all. So this question is asking how fast is this object going when this isn't compressed. The thing that people often get wrong here is if this is my third location, what's my H3? What's my height when it's right here, right before it touches the spring?
Is it 0.3?
It's 0, yeah, it's 0.3 if we don't change where 0. Because over here, we said that right here it was 0 and it's 0.3 meters above it. Now, could you go through and could you redefine your height? Sure, you could. You could change your H3 to be 0. But then your H1 would have to change. Your H2 would also have to change. So typically partway through a problem, not the easiest thing to do, it's doable, it's just typically not what we do. Assuming that no additional work was put in, and assuming no work all of a sudden started being done by friction, it's still a special type of two location problem. Or we can say our mechanical energy is conserved. We could say all the mechanical energy at location 1 is equal to all the mechanical energy at location 3. Because at any point along the way, they're going to be equal to each other. Or we could say that all the mechanical energy at location 2 is equal to all the mechanical energy at location 3. Also perfectly acceptable because mechanical energy is conserved at all points. So it really doesn't matter which one you compare it to, location 1 or location 2, but you're going to have to compare those two. A thing you got to be a little careful with when you start talking about like a second or a third location is you don't just want to pull numbers automatically from one side and say, oh, if my ME1 over here was 37.75, then I should be able to put 37.75 in here. And the answer is you can if you didn't cancel anything out. But if for some reason in one like two location problem you're able to cancel a mass, but in the next two location we're comparing location 1 and location 3, we now have a spring, we can't cancel mass. So you got to be a little bit careful about that. But the idea is once you go through and we set all this stuff up, the answer, and I'm not going to go through it unless someone really wants me to, but if you go through and you try this one on your own and you set it up, you should get an answer of 4.85 meters per second. And that's what at least that's what I got, and I hope that's what you get, because I think I did it right. It's just a new two location problem. That's really it. You just got to be consistent with your heights. That's typically the issue that people run into here. All right, any questions I can answer about that?
Yes.
Yeah.
So it would still just be PEG equals PE?
At location 3?
Yeah.
So I guess it depends, are we going to go location 1 and location 3?
Yeah.
Okay, if we're going to do location 1, everything cancels out like it did over there. So if we were to look at location 1 versus location 3, it'd be and those things still cancel out at location 1. Nothing's changed there. So it'd be PEG1, and then when you go through and we look at location 3, PE3, at location 3, there is a height. At location 3, there is no spring. And at location 3, it is moving. So it'd be PEG1 is equal to PEG3 plus KE3. And specifically, we're solving for the 1/2 MV3 squared. We're solving for that V within that K. But yeah, ME, that's going to cancel, obviously, because it's still not moving. And there is still no compressed spring. Assuming you don't redefine your height, which I don't encourage you to do. But. Other questions? I mean, I can plug in numbers and go through it too, if that's what you want. But. Okay. Then what you have today. Tomorrow we'll do probably a progress quiz, kind of checking in how we're doing with spring stuff. I do have a worksheet called Conservation 2 that I'll get you today in just a little bit. The very last problem on Conservation number 2, question number 6, it talks about a girl who is on a snow tube. I never give you the mass of the girl on the snow tube. The reason I never give you the mass of the girl in the snow tube, because in the end it works out that the mass cancels out. but I thought I had added it. We can say the girl is 50 kilograms. Okay, so if you're like, can I cancel the mass? 50 kilograms is the number, that would be a good one for you to use. So, the most common mistakes that people are making in this, like the very first problem, is dealing with that height being 0. Where is the height? Where is your height 0? Are you defining height to be 0? That's the biggest mistake that I've seen, and it's a conversation that should be had. So if you have a question on that, please make sure you're asking so we can kind of talk through that. And then this is, there's a definition in Canvas. I did cross off 5B, so you can ignore 5B, just for the record.